Okay, so next one is still related to Schedutil and how we actually control frequency, clock frequency from the scheduler and from the governor. This is about adding the scale deadline contribution to what we already have. Let's say that, deadline is already, at least the DL class, it's already accounted for, but we just go to max, like we do for RT currently. This is me and Claudio from Evidence. We basically work together on this set of patches. The patches are being proposed, shared on many lists. Anyway, yeah, so all this stuff that I'm going to talk about is based on Luca's bandwidth reclaiming patches that he presented yesterday, because basically we use one of the values that actually exposes with the patch. One thing that we introduced with this set of patches is frequency and CPU invariance. So like we have for the bell signal, for deadline, we need to be able to scale the reservation parameters considering the both frequency and CPU max capacity. What we want to scale is actually the runtime we provide to the task, so the amount of time the task actually has to available to complete. The idea is pretty simple. So we basically scale the original runtime by a factor which is linear with both frequency and CPU, which is the same basically rough assumption we make for when scaling the bell signal. For example, for frequency, it's pretty easy because we have the current capacity and the max capacity. We compute the ratio, and then the original runtime granted to the task is scaled by that amount. We actually have to do similarly to for considering CPU with different max capacity on, for example, big little systems.
So you're saying max capacity and current capacity. So you mean the max capacity on the local CPU?
Yes.
And
yeah. I mean, we first scale by frequency and then scale by CPU, like we do for.
Okay. Yeah, you're using the R scale.
Yeah.
Value.
Yes.
Okay.
Yeah. Yeah. So there are two subsequent scale. Yeah. Yeah. So this is actually pretty simple, but still have an example. This example run on an IT board which has 5 operating points, and this is actually the capacity. So capacity is the scale is 0, 10, 24. So for example, if I need to scale, so let's say I have a task which at the highest capacity it can run, is allowed to run for 12 milliseconds every 100 milliseconds. If we then run the task at the lowest capacity, its runtime is actually scaled up to 69 milliseconds. So we need to enlarge this thing. And in practice, this seems to work easily. So here, basically, I run the same task in different configurations. So this is basically running the task with performance governor. So that's the best case. The task that I put inside the scheduled reservation is a 10 millisecond over 100 millisecond task. So it basically has 2 milliseconds of spare time to run.
This is for deadline period.
Sorry?
This is for deadline period.
Yes. Yeah. It's an implicit, deadline task. And everything's fine for pair. Then if we run the task at the minimum frequency, the actual running time of the task will be going to 60 milliseconds, but then it has 69 milliseconds to complete. And actually this rule is working because if I then try to run the same task for 20 milliseconds inside the 12 millisecond reservation, it will be throttled after 69 milliseconds, which is basically what we expect. It's a pretty simple example just showing how the thing actually works.
What happens if you do your traffic setup for deadline scenario? You do it on max capacity?
Yeah, I guess the idea is that you want to come up with your runtime the period is the periodicity of the task, and then the runtime you want to evaluate and measure that considering the higher CPU at max frequency, because that's the reference, and then the thing will be scaled according to frequency and CPU.
But if you want to allow like deadline for multiple tasks,
Mhm.
you also on max frequency and
Yeah. The idea is that if you allow 90% of CPU, you reserve 90% of CPU capacity for your task, then you won't be able to scale down anymore. So the idea is that you allow task in, and then you account in the clock frequency computation in Schedutil, you account for the amount of bandwidth you actually allow to enter the system. So then you won't scale down, and everybody is happy, I guess. So what's the plan for start driving frequency selection for deadline? Yeah, the idea is that, as I was saying to you, is you want to scale clock frequency but still meeting task requirements, which the deadline, of course, are deadlines. Schedutil currently uses util average, so the PEL signal for sched normal, so CFS, and it goes to max as soon as sched 5 for sched deadline task enter the system. Using Lucas patches, we can use this new variable called running bandwidth, which is the active utilization which Luca was talking yesterday. This is actually my current implementation, but then Claudio will say there are different design choices we can make. This is one possibility. So yeah, you start using this as the sched deadline utilization contribution. And the other thing is that we need to move the triggering points that are currently in deadline because it just makes sense to make those triggering points some other places. So currently we have a single point in the tick, which doesn't make much sense for deadline because we don't actually do. I mean, we only enforce on tick. But basically, what we want to achieve is that as soon as there is an increase or decrease in the running bandwidth variable, we want to actually potentially trigger a frequency selection.
Yeah, and that's in the activation,
right?
And into the
In the zero leg.
zero leg.
Yeah. Basically, it's activation. Then I guess if the task is actually throttling because it tries to execute for more. Or if you go to sleep, but then we have to wait until
the inactive. I think it was blocked.
Sorry.
Blocked inactive.
Yeah. So we then have to wait. Yeah, we were discussing actually yesterday with Lorenzo and Luca. So currently, how it works, the zero leg. So yeah, when the task goes to sleep, you set the zero leg timer to fire at the zero leg time. So currently, what my patch implement is that at the point in time, you basically, let's say that the CPU went idle, then you just wake up and then to service the timer interrupt, and then potentially you trigger a frequency down, which might not make much sense. So we maybe want to ignore that, or I don't know. Anyway, that's what is currently implemented. I don't know. It depends. I guess it might make sense because you want, well, let's say if you are going to cluster idle, maybe you don't want to exit idle just to change the frequency because then you probably don't save much energy. Actually, you probably consume more by waking up, changing frequency, and going back than just the idle. It depends probably on in the particular state you are. I don't know. But anyway, that's what's implemented right now.
You wake up and reduce the frequency because the task is throttled now?
No, just because you basically release the so the grab mechanism release that amount of unused bandwidth for the others. So basically, you remove task contribution from this running bandwidth. So the task is not active anymore. You can, in principle, decrease your frequency at the point of time.
If there's a 1 millisecond delay to increase the frequency again, and you have a task that's like 210 millisecond reservation, you can't guarantee if you're going to
Yeah, that's another problem. I guess it's what also Thomas was saying before. If your task parameters are so short and strict that you can actually, and your frequency transition limit, the real hardware takes more than that to actually cope, you cannot play with this. The assumption here is that the hardware is actually fast enough to service your task requirements, which is, yeah, I guess, I mean, at least on the hardware that we are trying to use this for, seems a reasonable assumption. So yeah, I guess when the task wakes up, then you have probably 500 microseconds to actually reach the frequency, and then the task can run. So, and that amount of time you can actually consider that as overhead. So you want to dimension your task parameters considering that amount of little overhead that you have. Yeah, that's the assumption. So yeah, there is a big, I guess, the point of discussion. One of the big points of discussion is how to make the asynchronous k-worker thread responsible for changing frequency on ARM system actually work. Considering this, I'll just skip this for now. I'll discuss this later because like actually, yeah, Claudio maybe to comment on this.
Yeah. So just before continuing the discussion about the K-thread issue, I thought it was good to point out a couple of design choices that we have silently made, just in case some of you disagree or you have a different opinion on how to make this design. The first choice that we have made, as Luca yesterday said, his patch set keep track of two different utilizations for the run queue. There is the active bandwidth, which is the bandwidth of all tasks that are in active state, so not the tasks that enter the zero lag time or inactive state as in the grab terminology. But he also keeps track of the total bandwidth of each run queue, which accounts also for the inactive tasks. So the patch set keeps track of both the utilizations. So we can decide which one to use to set the frequency of the CPU. If we go for the active bandwidth, we actually implement the grab PA algorithm, which is more aggressive because you can reclaim the bandwidth of all tasks that enter the inactive state. So you can have a lower CPU frequency. Instead, if we track the total bandwidth, we have a more conservative approach, which could even work on the current deadline scheduler, providing that we add just such information about the bandwidth of the run queue. So it is less related to the grab algorithm. It just uses the information about the utilization of the run queue. Currently, in the patch set that Juri sent, we have taken the first approach by using the active bandwidth, so a more aggressive approach. The second choice is about which frequency to use in the runtime accounting when the update car hook is invoked on deadline. For a real-time purist, you should use the exact frequency for the accounting because you want your real-time task to get exactly the right amount of runtime that you want. So you should use the exact frequency, the exact CPU frequency that you have set on the CPU. And so you should be informed of each change of the CPU frequency that happens in the system. Actually, so ideally, deadline should be informed by each frequency change in the system, but this would introduce overhead and would be quite ugly. And also, if we prevent CFS from changing the frequency when there is some deadline load, still would be ugly and probably inefficient. So we have chosen to use just the current value of the frequency at the moment in which update curve is invoked. So this is slightly inaccurate because in the meantime the frequency could have been changed several times, and so you just use that the final frequency you see for accounting the runtime of the task. But at the moment, this seems to us the better approach. Again, if you think that we should take a different approach, just discuss it. So these are a couple of design choices, less important than the K-thread issue. So I think.
So with two, I'm not quite sure.
Sorry.
What would you want the notification for?
The idea is that let's say that you have you do your accounting on 10 millisecond bound. Let's say you have a tick every 10 milliseconds, which is not, but you can have that, and then your frequency changes actually more rapidly. Then you'll be using the last one when you're actually doing the accounting, or maybe in the meantime you actually, yeah. But I guess in practice, I mean, we probably don't have the problem much.
Yeah,
so it's just an approximation. So.
Yeah.
Seems fine.
Yeah, I told you. Yes. It seemed to us the best solution, the best approach.
Also, you may not be notified on all the
Yeah,
time.
yeah, of
Because,
course. Yeah, it would be crazy. Yeah. But we just wanted to highlight these two choices that we have made, just in case someone disagrees.
Yeah, I guess with the first one we can actually really play. I mean, it's easy to switch between the running and this bandwidth, and we might want to just see. In principle, you probably gonna save more energy with the first one. Might give just more, let's say, performance, or at least more guarantees with the second one. So I guess it's a matter of,
Maybe, I don't know, the first option is likely to cause many oscillations depending on the task set, I guess.
Yeah.
What about something in the middle? I mean, for correctness, you must increase frequency immediately when you have to. But in the opposite direction, maybe you can be more lazy. I don't know, what about some sort of low-pass filter? So you decrease more slowly, but increase immediately.
I guess that's still related to what Rafael was discussing.
Yeah,
so in the end, it's not only deadline, so it's actually the aggregation of deadline, CFS, and everything. So I guess we probably need some kind of filter at some level. And I guess this kind of filter can be placed like outside. I mean, this is just the signal you want to add to the others, and then of course on top of the aggregation, you can do whatever you want. So maybe yes. So yeah, that's probably a point in favor of the first one. So you want to be more, let's say, jumpy, but then since you are gonna aggregate with all the other signal, that's maybe good enough.
Yeah, but not only aggregation. I mean, you can be just slower.
Yeah, you can filter.
Because even with aggregation, you may still have useless oscillations, because the granularity of those tasks is likely to be quite fine.
Yeah.
So.
Yes.
I don't know if it can make any sense to consider the possibility to have like a safe margin that you always add on top of whatever is reported, just to account for possible variations that you cannot target.
So the margin usually it's built in the reservation parameters.
Yeah.
So you, as I was showing before, so if you have a 10 millisecond on the 100, usually you use 12 millisecond, 100 millisecond parameters, so that you actually trying to reserve a little bit more, because then you have to account for overhead or stuff that you cannot actually predict.
But this is not usually more related to the specific task that you are targeting. You are trying to account for possible variation in the task.
Yes,
Right.
and then but then you sum up all
You want to
the
factor in also the frequency in that one.
yeah, I mean, yeah.
Yeah,
But you don't have to
but in
actually-
that case, you are kind of allocating bandwidth, real bandwidth in the
Well, it's
CDS.
still a margin basically. It's the same if you are not the 10 milliseconds, you actually set 10 milliseconds, then you add 2 milliseconds as margin when you actually use that thing.
I agree, but this kind of margin is not really affecting the CPS allocated bandwidth. You do the proper computation considered without overestimating your task. Just to
That is
you add
true.
a little bit. You say, okay, if it's a deadline task, I accept to spend a little bit more energy eventually running one OPP over.
Yeah, it is true, but
One
still,
button.
since you still have to actually this a little bit of over provisioning for the task, even not considering frequency, so it might just be okay. Yes.
So this, especially one, is a variant of grub, where instead of allowing a task to overrun and consume more time, you preserve some more power. So
Yes.
what do you do when one of the tasks asks for the grub flag?
Yeah, so actually it was so indeed the patch that I actually have a big comment saying that I'm not sure what we want to do. Well, I guess the problem is that if you run it with performance or any other governor instead of Schedutil. So if you use Schedutil and you use the thing, you basically implementing group graph PA. So all the reclaim is actually goes to frequency, lower frequency.
Right.
So I guess it doesn't matter much. But then if you run the same thing with performance governor, then you want to actually implement the reclaiming between tasks. And how is implemented right now, we don't do it. So that's actually a question that I have to answer myself, what we want to do. I guess in that case, when you're running at least at a fixed frequency, then you want to actually implement, still implement the graph. So that's the accounting rule modified by Luca. When instead we are actually able to select the frequency with a Schedutil, then you just use the current capacity
So,
to do
so
the
grub
accounting.
has no guarantees that there is any idle time to reclaim to begin with. It's all optimistic, and given that the OPP is 1 over, you never select a frequency below yours. So there might always still be a little bit idle time. So you might just allow it to reclaim whatever there is.
It's very important.
And there might still be some, because even with the active bandwidth, that is fully accounting for the worst execution time, which is hopefully never actually met.
Yeah,
So
this is
you
the
might
point.
still have some idle time to reclaim.
Yeah.
So yeah, I would still allow grub to happen even with VA.
Yeah, makes
Whatever idle time there is.
sense. Yeah. It's easy to change that. Yeah, and yeah,
So
I
you can
guess
continue.
yes, sure. Yeah, last point is the big point. So yeah, what we do about this thing. So I don't know. I mean, thinking about also what Rappel was saying about the workarounds. To me, it might just be what we want to do in a short term to actually have something that people can start using, even if it's broken. But maybe it's probably fine for actually playing with it, and then try to find the real fix for the problem, like more time. But I don't know. It's
So Thomas, on the spybooks, they use as an intro. If it's busy, we can post the PMU packet in a queue. Once the intro comes in, sees this request from us, figuring it out.
We could do that, yes.
So that is all technically possible.
Yes.
Okay. And then once the PMU packet is out, we raise a timer, and then we wait a magic amount of time for the PMU to settle. And then we send the frequency packet, and Yeah, that's what I. That's how I understood this.
And then it makes room.
Yeah, shrooms.
So yeah, just maybe
Sounds like shrooms.
maybe because not everybody basically is has looked at the patches. So my current hack is to actually have this Sched special, which is set only for DK workers, which basically are put kind of on top of it's basically between the Sched deadline and Sched stop class. So those will preempt everybody because they are special, and there is no bandwidth actually associated with them because yeah, I don't know, I couldn't come up with a reasonable bandwidth because it doesn't probably make sense. And so they are just there to be able to, okay, if I have a deadline task that is actually running, and then I need to schedule this guy to actually change frequency for this other guy, then I want him to preempt, of course, the guy change frequency.
They are deadline tasks with an effective relative deadline of 0 and an infinite bandwidth.
Yeah, I mean, for this guy, actually, I don't use the parameters at all. They just preempt everybody.
But,
Yeah.
but they are effective with a relative deadline of 0
Yes.
with infinite bandwidth.
Yeah, I mean, from a theoretical point of view, of course, we cannot do anything with them, breaks everything. But my point was, yeah, from a practical point of view, might be a workaround for an issue. But
So
yeah,
that I think that's reasonable. I mean, from the practical standpoint, if somebody sees problems with that, then they need to
Buy better hardware.
or extend some delay somewhere to accommodate that device.
yeah, I mean, to me, there is a lot of value to try to see if we can, I don't know, fix this thing in the proper way. But while we're waiting for the fix to happen, maybe, yeah, we can have this.
Why not describe them properly as deadline task, allocating a specific bandwidth period?
How much
Maybe the period can be kind of figured out.
But the problem is that there is no reasonable bandwidth that you can set for it. So that would be like a best guess at best, right? Because how much if you don't complete the transition, then whatever you do next doesn't make sense pretty much.
Yeah.
So it has to be like
Yeah, I mean, ideally we want to actually have 100% of bandwidth so the task can actually run. But then if you actually associate a real 100% bandwidth, you're screwing the admission control. So you actually disturbing those CPUs.
Even a specific architecture or whatever is not possible to figure out what is really the requirements of these tasks. It's kind of platform dependent. There should be CPU.
Seems hard to actually achieve.
not in general.
And
They
then
probably tune things or measure and figure out for a single platform. But in general,
That's the key. The counter argument is that if you cannot really provide and find an upper limit, you can really screw up everything, which is deadline.
No, I mean,
you cannot really control how much this task will take.
well, I guess the assumption is that in practice doesn't happen. So it's the same thing that can happen with a real-time task today. So if you want to service on Android a real-time task, but then your hardware is not fast enough to actually serve the task, the real-time task is screwed anyway. And this is the same assumption. It's just a way to make frequency change possible for deadline as well. It's not more than the assumption is that it's practically working. So send it again. Let's see what
I still have them.
Yeah, I still need to change the. Yeah, so that's me again. Okay. That was it for us, I guess. Okay, so yeah, we have break until probably early.